class, Mr. Mohidian here with a video on how to understand and develop the trapezoid approximation method for definite integrals. So we'll do a bit of a review at the beginning. The first part you don't really have to write down until we get to the new rule. But just to review briefly, we have the left rectangle approximation method, the right rectangle, and the midpoint rectangle. We haven't talked much about this one yet in class. We will, though, next week. So the main idea is that when you divide a space like this from A to B into n subdivisions, in this case we have 3 subdivisions, one here, and one here, then there's essentially a choice as to which value to use to make your rectangle. So am I going to use A, or which I'm calling x0, or x1? Well, I'm going to choose the left of those values, and that determines my height. And then x1 or x2, I'm going to choose x1. So f of x1 is up here, and then I make a rectangle. On x2 or x3, I'm going to choose x2. And there's those. And I get some, I miss some, and I cover up too much as well. I over and I under approximate depending on whether the function is increasing or decreasing. I'll let you think about that. And likewise here you have x0 and x1, so I'm going to choose x1 because this is called the right rectangle approximation method. So I'm not going to use the first value, I'm going to use the second and all the rest. Here I'm going to use between x1 and x2, I'll use x2. And x2 and x3, I'm going to use x3. So you see that these are different approximations for the same curvy space. An alternate approach is to use the midpoint of each section, which is to say, find the midpoints of each of these and use that value to determine a rectangle. Midpoint here would be here, there's the y value, and make a rectangle with that height. Midpoint here, there's the midpoint y value, and make a rectangle there. One advantage is that these spaces are roughly the same. You gain some, but you also miss roughly the same amount. And this ends up being a pretty good approximation as well. A sometimes better approach is to use trapezoids, which we talked about briefly in class. So this is the new section. This is how we use trapezoids to better understand this space. So here I have a nice continuous curve. You can also say it's differentiable. It's smooth and it's also continuous. I'm going to divide this up into a couple of intervals. I'm going to call A, which is the beginning of my interval. I'm also going to call that x0 or x1. Then I have x0, then I have x1, x2, x3, and finally x4. So I'm dividing it up. I'm going to make 2 lines here to kind of indicate my y values. If I were to do a left rectangle approximation, then my left rectangle here would look like so, right? So I would have a rectangle right here. If I were to do a right rectangle approximation method, I would do a rectangle using x1, like so. And both have their advantages and disadvantages, as you can probably see. If I make this easier to see anyway. It's kind of hard to see at the moment. But a better approach really would be to connect the two and to make a trapezoid. So let me erase these extraneous lines. What I really want is to simultaneously use the left and the right, not to find a midpoint as we did a moment ago, but rather to make a trapezoid. Now this may not look like a trapezoid to you because of its orientation. We're typically used to trapezoids looking slightly different, but in a sense, this is a trapezoid. It is a trapezoid. So let's do a little bit of review over here. The area of a trapezoid is equal to the average of the bases times the height, which in a conventional trapezoid may look something like this. You have base 1, base 2, and your perpendicular height. Now our trapezoids, for this approximation, are going to sort of be rotated so that their bases, which are always parallel in a trapezoid, are oriented vertically. So here's base 1 and base 2, and the height is actually horizontal, right? So we have those configurations there. Well, with that in mind, our height actually is what we consider delta x. That would be the height, quote unquote, of each trapezoid. And the bases, right, these lengths right here are the y values associated with x0 and 1, respectively. So this distance right here we would call f of x0, and this distance right here we would call f of x1. That's how long it is. It's the numerical value of the function's output. So the area of trapezoid, I'll call this trapezoid A, the area of A would be 1/2 the bases, which are those two, they're averaged together. So 1/2 f of x naught plus f of x1 times the height, which is, curiously, delta x. So 1/2 the bases, average of the bases, times the height. That's the area of the first trapezoid. Fair enough. We now have a next trapezoid here from x1 to x2. I'm not going to choose the left. I'm not going to choose the right. Neither am I going to use the midpoint. I'm going to make a trapezoid with both values. Something like this, and that'll give us trapezoid B. So the area of B, well, it's going to be 1/2 average of the bases. I'll come back to that in a moment. The height is still delta x. And let's see. Well, x1 was the longer of the two bases here, but here it's the shorter of the two. In other words, it's being shared by both trapezoid A and trapezoid B. So we're going to visit our old friend f of x1 again, because that length is still there. And this length right here would be f of x2. So the average of those two. So keep in mind, this will pop up again a bit later, x1 is being used twice. And you can probably see that x2 is also going to be used twice. It's going to belong here, and then x3 is also going to be used twice. So that's going to belong here and there. So I'm going to pause the video here because some of it becomes a bit redundant. I'm going to go ahead and get the remaining trapezoids. So bear with me just a bit. Alrighty, so I went ahead and found the areas of C and trapezoid D here using the same basic idea. And I have them here, 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 and here. I also went ahead and strung together the total area. So the exact area is this by the Riemann definition, and it's approximately the sum of these trapezoids. Here's A, here's B, here's C, and couldn't fit it all, here's D. So you'll notice some commonalities in these terms. You'll notice, for example, that 1/2 appears in all of them. So 1/2 is there, here, here, and here, and likewise delta x appears in all of them. So for simplicity's sake, I'm actually going to factor those out. I'm going to factor out 1/2 delta x. Recall, and I believe I neglected to remind you of this, that delta x is equal to b minus a over n, where n is the number of subintervals or shapes that you're cutting it into. So 1/2 delta x comes from just factoring out all of these, and then that leaves me with everything on the inside, which is going to be the bases. So this, and this. So f of x naught plus f of x1 plus f of x1 plus f of x2 plus f of x2 plus f of x3 plus f of x3 plus f of x4. Almost had it perfect. Perfect fit anyway. Okay, well, curiously, you'll see that a bunch of them are used twice. x1's used twice, as we saw a moment ago. It's overlapping. f of x2 is used twice, and there you see it right there. f of x3 is also used twice. f of x4 and f of x naught are not used twice. So, in essence, what you have is the following. I'm going to simplify this as delta x over 2 as this right here. F of x naught plus 2 times f of x1 plus dot 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 everything up until f of x n minus 1 plus f of x sub n. So that's a lot to take in, but this right here is our trapezoid rule. Oops, couldn't see that, the trapezoid rule. It's a lot to take in, but this business here sometimes looks mysterious until you realize it's 1/2 times the height, and then these are the bases. Well, all but the first and the last base gets used twice, right? So the first base only belongs to the leftmost shape, the last base only belongs to the rightmost shape, everything else overlaps. It's kind of like a shared wall between two apartments or dorms. So f of x1 all the way up to the next to the last one gets used twice. So this means that all but first and last f of x values used twice, and hence the 2 showing that. So you will see this formula show up in class next week, and I wanted to give you some background on where it came from. Alrighty, see you in class.